So generally we have this harmonic distortion. So we after learning about class B push-pull amplifier, now we are going to see what is harmonic distortion, especially what is second harmonic distortion. Okay, so usually see the waveform will be linear. So when you have this distortion, it means that the system is going to be non-linear. When you draw the graph in output and input, you will get a straight line. But when the straight line is replaced by a parabola or a slope or a curve, you claim that there is non-linearity in your system. Non-linearity means other than your intended frequency, you have all these harmonics. See, I am speaking now to all of you. My voice will have one frequency. So if in your house you have a lot of disturbance, other than hearing my voice, you will hear all the other noises also, which are actually the disturbances. That is because there is some problem with either your headset, or some problem with your laptop, or some problem with your phone, or some problem with the network. It might be any reason. But other than my voice, if you are able to hear all other my voice with a lot of noises in the background, that is going to be distorted. Okay, that is going to be because of non-linearity of your devices. So my voice is also there. Other than my voice, you hear a lot of other voices. So that is all going to be the harmonics. So my voice is going to be the fundamental frequency. So harmonic distortion is mainly caused by non-linearity. See, non-linearity means output. Linearity means output proportional to input. Non-linearity means that is not the case. Output and input are not related at all. Okay, so the second harmonic distortion is determined from the transfer curve using 3 point. We are going to the second harmonic distortion plays a very major role in the distortion. So we are going to find out what is the value of second harmonic distortion. Okay, see, in class B push-pull amplifier, the second harmonic distortion is cancelled out completely, right? So we have only third harmonic distortion. See here, we have only this cos 3 omega t. We don't have 2 omega t, 4 omega t, because all are cancelled. That happens only in class B, but conventionally in all the transistors, you will have from second harmonic distortion. You have second, third, fourth, fifth, like that it goes on. So generally we usually find what is the value of second harmonic distortion. So you know that IC is equal to, generally IC is equal to beta IB. This relation we know, correct? It will hold good for a normal transistor. IC is equal to beta IB. I am going to write beta is going to be some constant K. So IC is equal to K1 into IB. This is for a normal, very good transistor. But when your transistor is going to have second order distortion, you have to include one more term, K2 into IB square. So IC is equal to K1 into IB plus K2 into IB square. K1 and K2 are going to be constants. And you know IB is equal to IBM cos omega t. So substitute IB here. So IC is equal to K1 into IBM cos omega t plus K2 into IBM square cos square omega t. So I am going to eliminate all these cos square into cos. So I am going to use this formula 2 cos square omega t is equal to 1 plus cos 2 omega t. Or I can write cos square omega t equal to 1 plus cos 2 omega t, the whole divided by 2. So when I substitute that, I get IC is equal to capital IC plus B naught plus B1 cos omega t plus B2 cos. This is the general format how you represent your distortion. You will have a DC current plus the DC term plus B1 cos omega t is your required frequency. B2 cos omega 2t. Here 2t is missing. B2 cos omega 2t is your second harmonic distortion. So from the graph, now I have to find the values for I1, B0, B1, B2 from the